Hello everyone, Mrs. Hansen here once again, continuing our lessons with a new topic on thermodynamics. I know we've just wrapped up our first module on thermochemistry, introducing the first law of thermodynamics, where we had said the amount of energy in the universe is a constant, that we cannot create matter or destroy matter, but we can change it from one form to another. We continue our investigation in thermodynamics looking at spontaneity. What does it mean when we say a reaction is spontaneous? If a reaction occurs without any external help, a reaction is said to be spontaneous. I know that with our first chapter, just coming off of Module 1, we introduced what we called enthalpy, the heat of a reaction, and we gave that an abbreviation of a delta H, the change in heat as reactants form products. We'll also introduce other thermodynamic properties. The next would be entropy, which just happens to get the symbol S. The entropy of a system is going to look at the dispersal of energy. How random or chaotic is the system? We'll investigate the second and third laws of thermodynamics in relationship to entropy and tie them to Gibbs free energy in our fourth section of our chapter. Gibbs free energy is going to be initialed with a delta G sign. So as we begin our thermodynamics lesson, we're looking at spontaneity as our first topic. And you can see from the visual here, this is a geyser out from Yellowstone Park. It is certainly a spontaneous reaction. It reads, geysers are a dramatic display of thermodynamic properties in nature. And what happens is the water inside the earth begins to heat up. And as it begins to heat, it rises to the surface through whatever small channels might be available in the ground. We see a huge pressure buildup until the water turns to steam, and that steam must be released. And so it's expelled forcefully through the hole in the surface. You can see this geyser, and it's something that you do not want to be around. It's hot, hot water. But it is indeed a spontaneous process, the focus of our first section. So these spontaneous changes occur in the direction that leads to equilibrium. And this is a topic that is coming our way for the next 3 chapters, believe it or not, the process known as equilibrium, where a reaction, instead of going to completion, we could say when A and B react, there is a forward direction producing products C and D, but there's also a reverse direction where C and D could be reacting back to the initial reactants A and B, though this is known as a dynamic equilibrium, where the forward and the reverse reactions occur. And again, that's going to be very specific to the next 3 chapters, so much more coming our way. When we think about the topic of thermodynamics, looking at the information to tell us if a reaction is spontaneous or not. Does the reaction occur towards the direction of equilibrium? Thermodynamics tells us if a reaction occurs. There is another driving force that tells us about the rate at which reactions occur, and that's going to be our very last chapter this term, called chemical kinetics. This gives us information about the rate of a reaction and how that reaction proceeds, known as a mechanism. Spontaneous reactions occur naturally. They are unaided. They do not need an input of any energy from an outside source to occur naturally. Non-spontaneous reactions do not occur without special input of energy, or a driving force, if you will. So thermodynamics, does the reaction occur spontaneously? Kinetics, well, how long does that reaction take to occur spontaneously? One is very different than the other. And I like this graph to show us the difference between thermodynamics, which is the topics of modules 1 and 2, and the term kinetics, which will be the rate of a reaction, which is the title of our very last module, module 7. The amount of energy exhibits by the reactants as compared to the products. This here, this difference in energy, is the study of thermodynamics. This is what we call the energy barrier between the reactants and products. We will label that the activation energy for the reaction. And to note that the higher the activation energy barrier, the longer the reaction takes to occur. And that's what this is telling us, the rate of a reaction. So we could see kinetics, this reaction versus this reaction. This one is a faster occurring spontaneous reaction, and this would be a slower rate, but yet they are both spontaneous, as the amount of energy contained from the reactants is higher than that of the product. So that would foreplay a spontaneous reaction. So these reactions that are said to be spontaneous, we know that they occur naturally under a certain set of conditions, and a non-spontaneous reaction simply doesn't occur without some sort of external push. It must be driven. You can get water, for instance, to decompose into the elements of hydrogen and oxygen. This decomposition reaction is non-spontaneous. No matter how long you stare at a cup of water, it will never just start on its own decomposing, and you won't see hydrogen bubbles and oxygen bubbles coming out. However, if you zap it with electricity, you electrolyze the water, you can force the decomposition of water. The external source of energy must be an input to force the reaction to occur, because it will not occur on its own. So keep in mind, the reaction that is spontaneous in one direction under this particular set of conditions is indeed non-spontaneous in the reverse direction. I like this graph as well to really emphasize the difference between kinetics, which is the rate of a reaction, how long does it take for reactants to turn to products, versus thermodynamics. Is the reaction spontaneous? Well, so for instance, this graph is portraying two spontaneous nuclear decays. The red line on this graph represents the nuclear decay of the uranium-238 isotope. This blue line represents the spontaneous decay of technetium-99. Elemental symbol for technetium is Tc. Clearly you see, as the days go by, 7 days, a week went by, the same amount of the radioactive isotopes, technetium and uranium, at initial time 0, you can see that the vast majority of the technetium-99 has decayed. However, I'm sorry, excuse me, got a little frog there. The uranium-238 looks relatively constant, doesn't it? And yet, this is a spontaneous reaction. It just takes thousands of years for a uranium-238 to actually decay, but it is spontaneous. And we can emphasize rate again with this graphic. Here is one of my favorite elements, carbon, in the allotrope of diamonds. Now, it is a spontaneous reaction for diamonds to turn into a different allotrope known as graphite. And this is just really a pencil lead, a piece of charcoal, coal. You can see that they are the same element. They're just organizing the atoms very differently. Now, when I say this is a spontaneous process, that means in comparison of the reactant to the product, there is an energy difference. I'm just saying that the rate of reaction is extremely slow, immeasurably slow, meaning this activation barrier, this energy barrier, is so incredibly large that the rate of reaction is very slow. And so, spontaneous? Yes, because there is an energy difference between reactants and products. That's the thermo part of our lesson. Kinetics? How fast does the reaction occur? Well, it could be very fast, like igniting a firework goes off instantly. Or very slow, such as carbon turning from diamond into graphite. Some more examples of spontaneous processes would include dissolving a soluble salt, such as ammonium nitrate. When ammonium nitrate, NH4NO3, starts as a solid, and you place that into a water solution, the aqueous ions of ammonium and the aqueous ion of nitrate dissociate from one another. They separate, creating electrolytes. This is actually an endothermic process, so the delta H would be positive, heat absorbing, and this is actually the compound found in a chemical cold pack. It gets cold to your touch. I wrote the word cold twice. A chemical cold pack gets cold to your touch because the system is absorbing heat from the surroundings, and therefore it's getting colder on the surroundings where your hands are. Another spontaneous process would include the expansion of a gas. We know that gases naturally diffuse to take the shape of whatever container they're in. They'll mix to form a homogeneous mixture spontaneously. Phase changes, such as ice melting, water evaporating, those are all examples of spontaneous reactions. When sodium reacts with water, sodium starts as a solid, is placed into liquid water, and you'll see instantly hydrogen gas come evolving out, forming a basic solution of sodium hydroxide. When that occurs, this is not quite balanced yet. What happens is you get a very violent, very exothermic reaction. Lots of heat energy is released. When iron rusts in the air, we form iron 3 oxide. Fe2O3 is named iron 3 oxide. And when this comes out balanced, this is also a spontaneous process. Clearly you see the kinetics for the sodium reacting in water is very fast. The kinetics for metal rusting is very slow, and yet they are both spontaneous reactions. Think about that gas diffusing and kind of look at this particular symbols with me. This diagram shows a valve closed, separating two flasks. One side with gas, the other is empty. And when you open the valve, the gas naturally diffuses to create a homogeneous, evenly dispersed throughout the entire volume. So when that happens, it's a spontaneous process. There is no change of energy because this is not a chemical change. It's just not a chemical change. It's just movement of molecules into a larger container. Here's that separation of aqueous ions from the salt as well. And know that this is just a physical change where we have a salt dissolving into water. And you can see that this is an endothermic process where the aqueous ions absorb heat energy from the water into the system, where the water is the surroundings and the aqueous ions are the system. So the evolution of heat is the delta H that we examined in our last chapter called enthalpy. It cannot be the only criterion in determining spontaneity. There must be another consideration to force reactions in the direction toward equilibrium. And let me kind of verify what we're saying. Delta H here is 0, no change in enthalpy, and yet this is a spontaneous reaction. Here, delta H is actually positive. This is an endothermic reaction where you see the reactants climbing the energy barrier, but the products end at a higher value in terms of energy. And yet this reaction is still spontaneous. How can an endothermic reaction, which is unfavorable energy change, how does it still occur? Or how does a reaction or a process that has absolutely no energy change still occur? Well, the answer is another process, another driving force is involved in spontaneous reactions. And we are going to study that second thermodynamic property known as entropy. Entropy is defined as the dispersal of energy. Very important. Here's a spontaneous process. Two objects at different temperatures are placed in contact. Heat flows spontaneously from the hotter object to the colder object. Why? It's not a chemical change. There's no chemical driving force, but there is a spontaneous process occurring, and that's entropy. The dispersal of energy from the hotter object to the colder object until an equilibrium is achieved. There's no net change of energy, but there is a dispersal of energy. So remember, two factors that will favor spontaneity. Thermodynamically favored. The first is enthalpy, the heat of reaction. Remember, we abbreviated that as delta H in our last chapter, enthalpy. Now remember, that's comparison of bond energies. So we had an exothermic reaction and we had an endothermic reaction. Exothermic, the system releases heat to the surroundings. And endothermic, the system is absorbing heat from the surroundings. And the second driving force of a spontaneous reaction is the entropy, the randomness versus order of a system. Systems want to disperse energy. Now, in general, enthalpy, delta H, is a much bigger factor in determining spontaneity. We know that exothermic reactions are favored. Most reactions that are spontaneous are exothermic. Endothermic is not favored. However, since some endothermic reactions are indeed spontaneous, there must be another factor playing a role in determining if processes are indeed spontaneous, and that's entropy. If entropy is positive, that is a favorable condition. That means that you are dispersing energy. You're creating a more chaotic, a more disorganized system. And if it is negative, it is an unfavorable situation, meaning that it's not leading towards spontaneous reactions because things are becoming more organized, or in other words, more concentrated energy in one place. Now let's keep practicing that idea of spontaneity. The dispersal of energy, known as entropy. In a spontaneous process, that energy is dispersed from the initial state to the final state is a favorable process. Dispersal of energy is favored. Now, to do that, the system moves to a higher state of disorder, right? Less organization creates a higher entropy. This thermodynamic quantity associated with the disorder is known as entropy, and it gets the letter S to designate its symbol. I don't know why S, but it is entropy. And that's going to be the focus of our second law of thermodynamics. It states that a spontaneous process results in an increase in the entropy of the universe. The universal amount of entropy increases. Now look at this spontaneous reaction. That's potassium being placed in water. Very exothermic. That is a favorable process. And it's actually creating more gaseous moles. And so the entropy is also favorable. That's the focus of our practices in this lesson. So to predict if a reaction is spontaneous, we have two variables to consider. We have the enthalpy and we have the entropy. Enthalpy is the heat of reaction. It's comparing bond energies of reactants and products. The entropy is the dispersal of energy, the chaotic nature of the system. The more randomly placed particles are, the more spread out they are, the more microstates they have, the more entropy the system observes. Look at letter A. What's happening here? This is a piece of dry ice, solid carbon dioxide. Dry ice, when placed with water, really is what you're seeing. It does it so on itself, but you start to see it bubble, and this is called sublimation. When a solid sublimes, such as carbon dioxide, that means it goes from the solid state to the gaseous state directly. It doesn't melt, it sublimes. Now, how is that an increase in entropy? Notice that the solids are highly organized at the atomic level. Gases are very dispersed at the atomic level. Because these are less ordered, more chaotic, you see that the gaseous phase is higher in entropy than the solid phase. Now, what's happening in letter B? A gas is condensing. So you can see that water is condensing on the outside of the liquid here. Now, to condense, that's going from a gas to a liquid. That's condensation. What happens to the entropy? Think about the atomic level, the molecular level of these molecules. In a gaseous phase, they are all disorganized. The gases take the shape of whatever container you have. They have the complete freedom to move around. Whereas a liquid is very organized. Not as much as a solid, but it is more organized than a liquid. A gas is less organized as compared to a liquid. Therefore, we had said this then would be unfavorable, that entropy is decreasing in this picture. Here we said entropy was increasing. When a solid went to a gas, that's a more chaotic state. That's a favorable change of entropy. However, when a gas converts back to a liquid, it's becoming more organized. So the entropy level is actually decreasing in that system. Now, what's happening here in letter C? This is just a test tube full of water. And what's introduced here is a little drop of food coloring. And as time goes by, you can see that the food coloring drop is dispersing. So the diffusion of the food coloring is creating a more chaotic state. Instead of being concentrated in one area, it randomly completes the entire volume of the water, and therefore entropy is going to increase. It's in a larger space, therefore dispersal of energy has occurred. Let me pause and grab a quick drink of water. The change in entropy for a spontaneous reaction is given by the following equation. That the delta S for a spontaneous process, keep in mind this is what we call entropy, is related to the heat of the system over the Kelvin temperature. The heat is what the letter Q stands for, isn't it? It's heat gained or heat lost by the system during the process. And T is the absolute temperature, which means it's on the Kelvin scale, no negatives. So that reversible process can be return to its original state, and that's what equilibrium is, going forward and reverse reactions. But if it's an irreversible process, we know that it can't. So for example, the breaking of a coffee mug into many pieces is an irreversible process. So the change in entropy for a spontaneous reaction, write this down, you'll need to know that formula. The change in entropy, delta S, is given by the Q of the system, that's Q for heat, divided by the Kelvin temperature. Now, just so you know, entropy is typically given in joules per Kelvin mole. And so you would have joules per Kelvin in that relationship. So, a microscopic understanding of thermodynamics. Entropy is measuring the extent of energy dispersal. Have I said that enough yet? Starting to stick in our mind that entropy is energy dispersal. In all spontaneous processes, energy changes from being localized or concentrated to being more dispersed or spread out is a favorable entropy, becoming more chaotic. Things in nature will randomly disperse to create a more chaotic system. So let's introduce the term microstate. And at the molecular level, it helps us to mathematically calculate entropy. The molecular scale statistical model of entropy involves a microstate. Let's define that term. A microstate is a specific configuration of the locations and energies of the atoms or molecules that comprise the system. For process involving an increase in the number of microstates, entropy is going to be positive, which is very favorable. However, if you reduce the number of microstates, it's becoming more organized, therefore the entropy is negative and it's unfavorable. The number of microstates are the number of possible ways you can distribute or disperse energy in the system. Let's keep talking about that. Let's consider the following case of a system comprised of n particles, capital N for the number of particles, distributed among n, lowercase n, number of boxes. The number of microstates possible for a system is n, which are the number of boxes, raised to the capital N, which is the number of particles. For example, let's take 4 particles. We have a red particle, a blue particle, a green particle, and a yellow particle. So 4 particles. Whoops. Sorry. And we're going to distribute those in 2 boxes. How many different microstates can there possibly be? So you can see 2 is the number of boxes. This is a microstate. Raised to the 4 gives us 16 possible combinations of distributing those 4, we'll call them atoms, if you will, those particles in different boxes. So for example, 1 microstate. I can place all 4 particles into 1 box, leaving 1 box empty. That's one possible way to distribute 4 particles in 2 boxes. What's the next possibility? Well, we can put 3 particles in 1 box and 1 in the other. And that 1 could be any of the 4 colors. There's 4 more microstates. We could actually put 2 particles into 2 different boxes. And the way that you can combine those colors gives us the next 1, 2, 3, 4, 5, 6 microstates. Red can be with green, red can be with blue, red can be with yellow, or all into this first box, or then you just repeat all those possible color combinations but putting them back into the second box. In the first box, we could have 1 ball, and the other box number 2, have 3. That gave us more microstates. And the last choice is to leave box 1 empty, putting all 4 into box 2. So here we had 16 possible microstates. Now, which one is the most probable way you would find the microstate of those 4 particles? Well, it's the one that has the most chances to occur. The most probable configuration is the one where these 6 statistically equal opportunities occur. You're more likely to find 2 and 2 than you are with 0 and 4, just because there's more possibilities of arranging it that way. So the most probable distribution, therefore, is the one of greatest entropy, and that would be the 2 and 2. So entropy increases logarithmically with these number of microstates. Instead of looking at particles, here's an example where we're looking at energy. All right, so let's figure out what we have. Notice that the little circles around the particles represents packets of energy. So there are 2 packets of energy. One microstate is to place both energy packets around the first particle. 1, 1. Particle 1 has 2 units of energy. Then what? I can give 1 unit of energy to 2 different particles. I can give it to 1 and 2, 1 and 3, or 1 and 4. I can then put both packets of energy around particle 2, so you have both packets on the same one. You can do that for particle 3 as well, and you can do it for particle 4. Place both packets of energy around. And again, I can disperse them, 2 and 4, 2 and 3, 3 and 4. All of those possible combinations of looking at dispersal of energy. So there are 10 microstates represented in this system. Possible ways to distribute. So let's think about that. You're going to put 4 particles in a container. So let's say we have particle that's color-coded black. Here's one that's purple. Here's one that's blue. And how about a red? 4 particles in a container with 6 quanta of energy to disperse. So, my goodness, you could put it 1, 2, 3, 4, 5, 6. All quanta of energy around the first particle. Keep thinking about that. How many microstates are possible? And before you begin drawing, just convince yourself that there's lots of microstates possible. So much so that I'm not going to draw them all, my goodness. But look at what we can come up with. If we have 4 particles separated from each other, 2 particles that have 3 quanta of energy and the other have 2, and the other 2 have none, a total of 6 quanta of energy will be distributed once the 4 particles interact. Look at all the different microstates. There's a total of 84 possible combinations to have this dispersal of energy occur. More than we'd ever be asked to figure out. Here's the point of my story. Remember when I had 4 particles and 2 quanta of energy? With 2 quanta, I'll just do like this. We had 10 microstates. Look how quickly things change as soon as we start adding more and more particles of energy, particles and quanta of energy into the system. Entropy quickly rises. The more and more particles, the more and more energy to disperse, the more we'll see that entropy can disperse that energy in these microstates. So that amount of energy that was dispersed from 2 to 6 resulted in a number of microstates that changed from 10 to 84. You'll never be asked to draw all possible combinations. That's too much. But what we're walking away with is understanding that the number of particles and or quanta, as that increases, the microstates grow rapidly. So what are some things that influence entropy? The phase of the substance. Is it in a solid, which those are very highly organized? Is it a liquid, where the molecules are still, have strong intermolecular attractions, but they do have the ability to flow past each other? Or are they in a gaseous phase, where there's complete independent motion? The gases would have the highest entropy, the more disorganized system, as well as temperature of the system. Think about temperature as being directly proportional to the kinetic energy, right? So hotter objects move faster, their velocity is faster given the same temperature as a heavier object. So those higher temps mean they have greater freedom to move around. Think of this solid, very organized, then a liquid, less organized. Then the gaseous phase is very, very unorganized. The entropy is increasing in the system as the molecules become less organized. Think about that in terms of temperature as well. Entropy is increasing as the molecules begin to gain heat energy. Even if they're in the solid phase, those atoms are going to be wiggling and waggling in their atomic bond. Then here, of course, we see a phase change occur, so no change in entropy there, or no change in temperature there. Entropy is increasing as solids turn to liquids. The liquid then goes from 0 to 100 if it's water, and then you'll see it begin to boil and turn into the gas. Entropy will increase as the temperature rises during those phase changes. So solids, liquids, and gases. If you think about the entropy as being a measure of energy dispersal, gases are the most disorganized state of matter and therefore present the highest form of entropy. Comparing liquid water entropy value in a joule per Kelvin mole, approximately 70, and water gas, which is steam, about 189, significantly higher entropy as it moves into the gaseous phase. And it also, when we see the size of the container increasing, the number of microstates accessible to the system also increases. Therefore, the system becomes more chaotic, more spread out, more dispersed. Therefore, the entropy increases. Ludwig Boltzmann stated that as the number of microstate increases, so does the entropy of the system. There is a direct relationship between entropy and the number of microstates. Write this down and know this formula. That entropy is set equal to K, which is a constant. It's known as Boltzmann's constant, and it has a value of 1.38 times 10 to the negative 23rd power joules per Kelvin. I don't need to derive that. It would involve graphing. Then the natural log of the number of microstates. The natural log is Ln on our calculator key. That's the base unit of Euler's number. It is very different than a logarithmic base 10. So notice that it's not log that uses the base 10, but rather the natural log that uses the base of Euler's number. So natural log of W, where W is defined as the number of microstates of the system. Entropy is equal to K, Boltzmann's constant, times the natural log of W, where W is the number of microstates. Can I make just a comparison here? Last chapter, we said that in the first law of thermodynamics, the amount of energy in the universe is a constant, and it's found with the relationship of heat and work. This is a lowercase w. And so in thermodynamics, the W of lowercase is relating to the first law of thermodynamics, representing work. Work done on a system or work done by a system. Remember, this is heat. Heat is either endothermic or exothermic. And E is, of course, energy in the universe. The amount of energy in the universe is a constant, first law of thermodynamics. Now, I say that because this is W is a capital W, where that in thermodynamics represents the number of microstates. This relationship allows us to predict how many microstates are possible if we know the standard entropy value. And again, these are thermodynamic properties published in our appendix of our e-text. You found these for delta H of formation. In our last chapter, we had to look up delta H of formation. And so in this chapter, you're going to look up delta S, standard entropy, and in a little while you'll notice we look up delta G, Gibbs free energy standards, all in the same table, the thermodynamic properties table in the back of our e-text. One of the appendix there gives us those values. So the standard entropy values are published in standardized tables. You do not need to memorize those. To calculate the change in entropy for a system going from a condition with 5 accessible microstates to 30 accessible microstates. This is our example problem. How many microstates did we say? Well, it's going from 5 to a total of 30. We want to know the change in entropy for a system going from 5 to 30. Well, we need Boltzmann's constant, 1.381 times 10 raised to the negative 23rd joules per Kelvin, times the natural log of 30 over 5, which we know is 6. So grab your calculator and let's see if we get a constant answer. Be my calculator, buddy. Hit with me. So I'm going to take the natural log of 30 over 5, just so we can see that was simplified. And my screen says like 5.0106 and so forth. I don't need to write that. I'm just going to hit that first and then times that by Boltzmann's constant, 1.38. Use your scientific notation key, EE, negative 23. And the answer here comes out to be 6.9. There's 3 decimals there, so I'll carry 3 decimals of Boltzmann constant, 915 all round. And that's times 10 to the negative 23rd joules per Kelvin ends up to be our unit. There is your entropy. Now let's see if that number makes sense. You're going from 5 microstates to 30 microstates. More microstates, there's a direct relationship, is an increase in entropy. So therefore, our number should come out positive, and it did, because entropy was increasing with an increase in the number of microstates. Had we flipped that, if we were becoming more organized and we went from, whoops, I want to flip it, from 5 over 30. If we started with 30 microstates and now only allowed them to have 5 microstates, what would that come out as? If you hit that with me, the natural log of 5 divided by 30 times your Boltzmann's constant, that gives us 2.474 times 10 to the negative 23, but it came out negative, didn't it? Because it's becoming more organized. So the negative here is a decrease in entropy, which is an unfavorable process. Yeah, good work. Here's a homework problem looking at dice. Let's give this a read through. With 2 dice, each numbered 1 through 6, there are 2 possible ways to roll a 3. Those would be 2 microstates. One way you can roll a 3 on 2 dice is to roll a 1 and a 2. Let's call that dice 1 and dice 2. Or dice 1 can be the 2, dice 2 can be the 1. Those are the 2 possible microstates to roll a 3. For the outcome of a 3, there's 2 microstates. That's what we're saying. How many possible ways are there to roll a 6 with 2 dice? Let's draw that through. Dice number 1, dice number 2. I could have a 1 and a 5. That gives me a 6. But I could also have a 5 and a 1. Those are 2 different microstates because those are 2 different dice. What else can we do? Well, what if dice number 1 and dice number 2 had 3 dots? I think they're like this on a dice. That's another possible microstate. What else? How about a 4, and a 2, or a 2 and a 4. Two different microstates, two different dice. We did 1 with 5, 5 with 1, and it went to a 2, then we went to a 3. So that's it. We have 1, 2, 3, 4, 5 possible microstates. 5 possible ways you can roll a 6 with 2 dice. What is the entropy associated with an outcome of 6? Well, our formula says that entropy can be calculated by using Boltzmann's constant times the natural log of the number of microstates. So the entropy of the system would require taking Boltzmann's constant, which we'll just round to 2 decimals, and the unit there is a joules per Kelvin, times the natural log of the 5 microstates. And what do you find when you hit that? I'll do it with you. 1.38 times 10 to the negative 23rd times the natural log of 5. And my screen reads 2.22 times 10 to the negative 26. And that answer is a positive number. And that's joules per Kelvin on the entropy unit. We calculated entropy knowing the number of microstates in the last 2 examples. Now, other ways we measure entropy include looking at how heavy the molecular mass and the general complexity of the molecule itself. So, for instance, the simplest hydrocarbon of all, with its tetrahedral electron geometry there, it's molecular geometry, tetrahedral, CH4. It has an entropy value of 186.3 joules per Kelvin. Now, the next simplest hydrocarbon would be ethane. That's 2 carbons connected in a row, each of those having tetrahedral molecular geometry around their central atom. But the molecular entropy for this more complex, the heavier molecule, increases to 229.2. Now think about that. There must be more microstates. And that's because bonds can rotate, can't they? Bonds twist and turn if they're single bonds, and therefore have more possible positions in space. The next molecule is a 3-carbon chain called propane. Propane, with its 3 carbons, all of tetrahedral shape, have more possible microstates. These bonds can twist and turn. More possible arrangements in space give it an increase in entropy. So as molecules get bigger, they get larger, they contain more bonds, they get heavier, all of those contribute to greater dispersal of energy and therefore a higher value of entropy. Entropies of ionic solids can also depend upon the Coulombic attractions. And what does that mean? Take, for example, a magnesium oxide crystal, where magnesium carries a +2 charge and oxide carries a -2 charge. Compare that here with a sodium fluoride crystalline solid. Why is it that the +1 -1 has greater entropy as compared to the +2 -2? It has to do with those Coulombic attractions, right? The charges. The +2 charge and the -2 charge have a greater attraction for each other. A larger magnitude of charge creates a greater attraction. Therefore, it has a tighter bond. They're closer together, and therefore, it keeps them from moving. They're in a more fixed position. The higher the charge, the more rigid their bond. Whereas a +1 -1, they're less fixed, more able to move in that position. So they're held less tightly and therefore have a greater entropy. So the higher charge is a more fixed position, can't move, therefore it has lower entropy than salts that have lower charges. So as we bring closure, we kind of opened up the section here and thought about the first law of thermodynamics and introducing this with the second law of thermodynamics. I'm going to ask you to pause and think. On your test, you'll be asked these questions. What does the first law of thermodynamics say? What does the second law of thermodynamics say? Pause the video and write down your answers right now into your notes. Come back to me when ready. I hope you wrote something like this. With our first law of thermodynamics, we said energy cannot be created nor destroyed. It can be converted from one form to another, but it is conserved. The amount of energy in the universe is a constant. It is related by heat and work. Heat is Q, endothermic and exothermic, and the amount of work either done on the system or by the system give us a constant amount of energy in the universe. Now, the second law of thermodynamics is what we've been spending the vast majority of this lesson on. For a process to be spontaneous, the sum of the entropies of the system and the surroundings must increase. To say that simply, entropy of the universe increases for spontaneous reactions. Second law of thermodynamics says if the entropy of the universe is greater than 0, it's a positive value, the reaction would be spontaneous. If the amount of entropy in the universe decreases a negative value, it is not spontaneous in the forward direction. And if it is equal to 0, reversible reactions are occurring, that we have a forward reaction at the same rate as an reverse reaction. The system is said to be in equilibrium. And I've mentioned to you that the equilibrium is the topic of our next 3 chapters. But I really wanted to emphasize focusing on what those laws are saying. And there'll be a third law of thermodynamics in a little while in our further up lessons in this unit. But a good time to reflect upon what those laws are bringing us. The system, the part of the universe that's interesting to us, and the surroundings or everything else. Kind of a nice broad definition there. That second law of thermodynamics, very important to remember, spontaneous reactions show a positive entropy for the universe. Non-spontaneous processes show a negative entropy. And if the entropy is at 0, the process is in equilibrium, emphasizing the second law of thermodynamics. And let's bring some practice as we close out this lesson. Which reaction produces an increase in entropy? I'd like to talk about how I would tackle this problem. I know that gaseous moles have the highest entropy. And so I just wanted to write that note with you there. So what I wanted to do is to recognize in this first choice, I have 1 gaseous mole of nitrogen reacting with 3 gaseous moles of hydrogen. So on this side, we have 4 gaseous moles pointing at, well, there's only one product here, 2 gaseous moles. 4 gaseous moles is more chaotic. So what happened to entropy here? It became more organized, didn't it? When 4 gaseous moles recombine to only make 2 gaseous moles, this is a more organized system. I'm trying to write and spell. Therefore, delta S is negative, and that's unfavorable. It's becoming more organized. How about here? We have liquid water going to solid water. Well, again, solids are more organized, aren't they? Those at the molecular level, the water molecules are held in a fixed, rigid position. So therefore, this process would also be an unfavorable negative entropy. Here I have 2 gaseous moles on the left side, over here pointing to 2 gaseous moles on the right side. If 2 still remains as 2, delta S is actually at a 0. There's no change in entropy, and therefore we would call that an equilibrium process. Here's one. Notice that a solid is turning into a gas. When a solid goes to a gas, it is becoming more disorganized. And here again would be our find an entropy value that is becoming more disorganized. The rigid fixed conditions of the solid atoms of carbon dioxide turning into a complete freedom of motion in the gaseous phase. And last, we have 2 aqueous ions of silver and chloride forming a solid that's becoming more organized. Aqueous ions are swimming around in water, right? Freedom to move. They're dissociated in a water medium. So you have the movement of aqueous ions. Those are electrolytes. And over on the solid side, those become fixed, rigid positions. So that's an unfavorable entropy. So we were asked to find which one of them increases in entropy. In this practice test example, we found one right here, becoming more disorganized as the system turned from solid into the gaseous phase. Why don't you try one now? Pause the video and answer this question, going through each example until you find the one that shows a positive entropy. What did you find? Here we have a liquid, a gas turning into a solid. Delta S is negative. It's more organized. It's an unfavorable reaction, unfavorable process. Here we have 1, 2, 3 gaseous moles converting into 2 gaseous moles. Well, again, that's more organized, so that's a negative entropy. Here we have 2 gaseous moles converting into 1 gaseous mole. That's more organized, isn't it? That's a negative entropy. Here we have a gas turning into a solid. That's also an unfavorable process. But look here. A solid has dissolved and separated to create aqueous ions. So here, with those electrolytes swimming around in that water with complete freedom to move around their aqueous medium, we have a positive entropy. This is more chaotic, more disorganized, and therefore a favorable positive entropy. That's the one you selected, I'm sure. Shall we keep practicing? These are old test questions. Find the one where entropy is negative for this reaction. Pause the video and put up your guess. All right, welcome back. Let's check. Here we have 1, 2, 3 gaseous moles converting into 2 gaseous moles. Well, that's becoming more more organized. Therefore, the entropy is negative. Let's continue to be sure we've got this correct. Here we have 1 gaseous mole converting into 2 gaseous moles. Well, that is more chaotic, so that's a favorable positive entropy. Here we have a solid converting into 2 gaseous moles. Gases, of course, we know are more chaotic. That's a positive entropy. When a solid separates into its aqueous ions. That's a favorable entropy. Here the ions are held in fixed positions. Here they're separated and floating around in the water. And when a liquid turns to gas, that is a positive entropy. Gases are more chaotic in their nature as compared to the fixed positions of water in a liquid form. So right off the bat, we found that as our example of negative entropy. And that means it became more organized. Which of the following linear chain alcohols is likely to have the highest standard entropy in the liquid state? This goes back to the complexity of molecules. Do you remember what we learned? Which one would you pick? Well, just like you, I'm going to pick the longest carbon chain, the heaviest molecule, to have the highest standard of entropy. All those single bonds have freedom to rotate and move around, giving the longer molecules more complexity, more microstates. And that's easy, isn't it? Just finding the longest, heaviest chain. This makes a perfect place to stop. Take a break from your lessons. When ready, come back for the third law of thermodynamics.